Hello and welcome to this introduction to the Synchronous Digital Hierarchy, or SDH as it's known for short. This video has been produced to give you a basic introduction to the BT SDH network. We'll look at its component parts and I'll introduce you to some basic SDH terminology. The video is split into 4 sections. These are SDH principles, the SDH core network, network management, and Access SDH. I suggest that you stop the tape between each section and have a look at the supporting material that's supplied with the video. Now you'll be familiar with the existing plesiocronous digital hierarchy, or PDH. So what is SDH? Well, the synchronous digital hierarchy is a series of internationally agreed standards which define a new generation of managed transmission networks. But what do we mean by synchronous? Well, to prevent loss or corruption of any data, all pieces of equipment in a synchronous network are locked to a common clock. For the BT SDH network, this is achieved by deriving primary timing signals from the Global Positioning System, or GPS. Timing is then distributed via the SDH network to each piece of SDH equipment. Now you may be wondering, why is BT investing in SDH? Well, there are a number of reasons, so let's take a look. PDH circuit provision is time-consuming and labour-intensive. Circuits through an SDH network can be provided in minutes. Our PDH equipment requires loads of room. Equivalent SDH equipment is more compact. With PDH there are lots of physical connections. SDH connections are software controlled. PDH alarm information tends to be crude and localized. SDH alarms are very detailed and centralized. PDH failures usually require manual intervention. SDH can be self-healing. PDH is designed to different standards across the world. SDH meets international standards. In summary, an SDH network is more reliable, less costly, and easier to manage. But before we look at any SDH equipment, let's take a look at the synchronous digital multiplexing hierarchy. This first graphic shows the SDH hierarchy as implemented by the European Telecommunication Standards Institute, or ETSI for short. Hopefully you'll recognise the bit rates on the right-hand side, as these are used in the PDH network. However, you may have noticed that the 8 megabits per second is missing. This bit rate is not supported by SDH. To explain this hierarchy, we'll look at how a 2 megabits per second signal is dealt with. An incoming 2 megabit signal is chopped into manageable chunks called containers. Each container then has some additional data added called the path overhead. This is control information and allows us to monitor the performance of the circuit. Once the path overhead has been added, the signal is referred to as a virtual container 1-2, or VC12. Where the 1 indicates that we're at the first level in the multiplexing hierarchy, and the 2 refers to the original 2 megabits per second signal. A pointer is now added to form a tributary unit, or TU12. One purpose of this pointer is so that a distant multiplex can locate the TU12 signal within a higher order signal. 3 of these TU12s are multiplexed to form a tributary unit group 2, or TUG2, where the 2 indicates that we're now at the second level in the multiplexing hierarchy. 7 TUG2s are multiplexed to form a TUG3, which is the third level in the hierarchy. Now a TUG3 can also be formed from a single 34 megabit per second signal. 3 TUG3s are multiplexed to form a virtual container 4, or VC4. Alternatively, a VC4 can be formed from a single 140 megabits per second signal. A VC4 is called the payload, and it contains the original traffic and the path overheads. Section overheads are now added to form a synchronous transport module 1, or STM1. These overheads are required to provide the comprehensive network management functions which we'll see throughout this video. They're a major benefit of SDH. STM1 is a fundamental building block within the synchronous digital hierarchy and has a transmission rate of 155.52 megabits per second. Earlier I said that one of the advantages of SDH is that it conforms to internationally agreed standards. This graphic shows the hierarchy as implemented by the American National Standards Institute, or ANSI. And if we now bring back ETSI standard, you can see the full hierarchy as defined by the International Telecommunications Union, or ITU. But to keep things simple in this video, we'll remove the ANSI hierarchy and we'll concentrate on the ETSI standard. Just before we leave this hierarchy, see if you can work out how many signals of each bit rate can be carried in the VC4 payload of an STM1 signal. Have you worked it out? Well, let's have a look at the VC4 payload. It can carry a single 140 megabits per second signal, 3 34 megabits per second signals, 63 2 megabits per second signals, or a combination of 1 34 megabits per second signal and 42 2 megabits per second signal, or 2 34 megabits per second signal and 21 2 megabits per second signals. This first section of the video has contained a lot of information, so we suggest that you now stop the tape and have a look at section 1 in the supporting material. In this section of the video, I'll introduce you to some of the equipment that forms the SDH core network. These pieces of equipment are called network elements, and we'll look at add-drop multiplexers, digital cross-connect switches, and line systems. Firstly, the add-drop multiplexer, or ADM for short. Let's consider an STM1 ADM and what this does. Well, there are two line cards that will terminate signals at STM1. These line cards are identified as line card west and line card east. The ADM also accepts a number of tributary cards. In this example, 4 2 megabits per second trib cards have been provided, and as each card will support 16 2 megabit circuits, 64 2 megabit ports are available. Now, by the use of an internal switch within the ADM, lower order paths can be connected from one line card to the other line card, channel for channel, or connected to different channels. Signals may be dropped or added via tributary cards as shown here. It will also allow one tributary port to be connected to another. All these connections are software controlled from the Network Management Centre and don't require a site visit. The pictures we've used here show the Marconi SMA1. There are other add-drop muxes such as the SMA4 and SMA16C+. These units are both physically bigger and can carry a larger capacity, but basically they perform a similar function to the SMA1. Now that you're familiar with add-drop muxes, let's see how they're deployed to form the basis of the SDH core network. ADMs are normally connected in rings. In this case, 6 ADMs are connected using pairs of optical fibres. The reason for this, as you'll see shortly, is that it will allow us to protect circuits if required. Let's look at the routing of a typical 2 megabits per second circuit where both ends terminate on the same ring. As you can see, the circuit starts at ADM A. Here the traffic is applied to a 2 megabit tributary port on the ADM. The signal is cross-connected and then multiplexed as channel 25 in the VC4 payload for transmission to ADMF. In ADMF, the path for our circuit is connected channel 25 to channel 25. At ADME, the tributary unit arrives as channel 25 and is cross-connected to channel 16 for transmission to ADMD, where the circuit then terminates. At D, the tributary unit arrives as channel 16 of the VC4 payload. The signal is demultiplexed, cross-connected, and the traffic is presented on a 2 megabit tributary port. We can now see that this circuit has a single routing one way round the ADM ring. If we wish to protect this circuit, we can simply route the traffic both ways round the ring simultaneously, like this. The signals are then monitored at the receive end, and should the signal from what is designated as the main path be degraded, the ADM will automatically switch to the alternative path. This is known as sub-network connection protection. I'll come back to talk more about protection later. Now that we've seen an ADM ring, you might be wondering, how do we actually feed a circuit to a customer? Well, the ADMs that we've just looked at would normally be installed in BT premises, but we can take the same unit and install it in a cabinet at a customer's premises. The unit would be fitted with a line card west and fed over a pair of optical fibres connected to an optical tributary card in an ADM. In this case, the multiplexer at the customer's premises is called a terminal mux. You can see here that there's only one route from the customer into the ADM ring, and therefore the customer's circuits can't be fully protected. Customers who need full end-to-end protection for their circuits will require another completely separate route into the network. This is done by fitting a line card east at the customer's premises, which, as you can see, is fed from a different ADM in the ring. This is called dual parenting. The ADMs that we've looked at so far are very sophisticated pieces of equipment, so cheaper alternative methods of delivering SDH to customers have been developed. This one is known as the Marconi SDH extender and was formerly called the Virtual Container Transport System, or VCTS for short. This can be used where the full STM1 payload isn't required. The system consists of a Virtual Container Access Module, or VCAM, which is fitted in a trib slot of the parent ADM, and a Virtual Container Terminal Module, or VCTM, which is installed at the customer's premises. As you can see, this is a smaller unit and can be desk or wall mounted. This time the link between the VCAM and VCTM is via a single optical fibre. The VCTM can also be dual parented to provide full end-to-end protection if required. Access SDH is another way of serving customer premises, and we'll look at that later. We've now seen how a customer's premises can be connected to an ADM ring, but a customer may want a circuit between two premises fed from different ADM rings. So let's look at how ADM rings are linked to form a core network. At major BT nodes we have SDH digital cross-connect switches, or DXCs for short. These are connected in a mesh to form a core network. At the cross-connect sites there are in fact two types of DXCs. These are called the 4.1 and 4.4. The 4.1 is a combined multiplexer and digital cross-connect switch. Ports on the switch are at STM1, but the 4.1 will demultiplex the STM1 signal and then switch circuits at tributary unit level. In other words, a 2 megabit circuit arriving in the payload of one STM1 signal can be cross-connected to the payload of any other STM1 signal on the switch. This is sometimes called traffic grooming. As you can see, the 4.1 cross-connect consists of a number of racks of equipment. The 4.4, however, is purely a cross-connect switch. Again, the ports on the switch are at STM1, but it can only switch the entire payload of one STM1 signal to another STM1. In other words, this switches at VC4 level, and you can't switch an individual circuit within the VC4. Again, the 4.4 is a number of racks. Of course, all this switching is remotely configured from the Network Management Center. It is the 4.1 switches that have STM1 links to ADM rings as shown here, and for protection, ADM rings are dual parented off a second 4.1 switch. It is the 4.4 switches that are connected in a mesh configuration to form a core network of VC4 highways. To simplify the diagram, we'll consider the 4.1 and the 4.4 to be a single switch. These DXCs are some distance apart, so this is where we can use line systems. SDH line systems have a number of STM1 tributary ports. The tributary signals are multiplexed to form an aggregate signal for transmission over an optical fibre cable. The DXCs are connected in a mesh using STM16 line systems, and as you may have guessed, these systems will carry 16 STM1s. Looking back at our diagram of the network, let's consider a circuit between customer A and customer B. Earlier I mentioned protection, so let's now provide an alternative route for this circuit. As you can see, the two routes are totally separate until they arrive at the customer. Therefore, this circuit has full end-to-end protection. Although the diagrams we've been looking at are a convenient way of looking at the network, the BT network is actually arranged in tiers. Tier 4 is the customer's premises. Tier 3 consists of nearly 300 local ADM rings. Tier 2 consists of approximately 160 regional ADM rings. Tier 1 is the inner core network of 50 interconnected cross-connects, with 25 rings of ADMs called supercells providing an intermediate layer between Tier 2 and Tier 1. Finally, Tier 0 connects the international frontier stations and carries international traffic. Again, there's been a lot of information in this section of the video. I recommend that you stop the tape now and have a look at section 2 in the supporting material. Throughout this video, we've seen that one of the major benefits of SDH is centralised management. In this section, we'll have a look at this in a bit more detail. The BT SDH network is managed from a small number of network management centres, or NMCs for short. In fact, if there was a major problem, SDH can be managed from just one of these NMCs. To manage the network, the NMCs are connected via a data communication network, or DCN, to element managers. The element manager for a cross-connect is called an Operations Administration and Maintenance Terminal, or OAMT. Element managers for ADMs and line systems are known as EMOS. This stands for Element Manager Operating System. As you can see, for protection, the EMOS for an ADM ring is connected via two gateways. Other ADMs in the ring are managed via the STM1 overheads. Back in the NMC, there are a number of subsystems used to manage this network. We'll look at just two: PAX and Fault Manager. PAX stands for Planning, Assignment and Configuration System and is a database model of the complete SDH network. As its name suggests, this system is used to plan, assign equipment and remotely configure circuits through the network. In other words, by using PAX we can provide circuits over the SDH network without having to visit any station along the route. PAX can also provide a visual representation of the network by means of a graphical browser. But what about when things go wrong, which they do from time to time even with SDH? Well, Fault Manager receives all network alarms. And as you can imagine, with a major fault, lots of alarms are generated at the same time. But the software also performs alarm correlation, and this will attempt to provide the root cause. This should enable the NMC to send the right person to the correct location to fix the fault. Here we've only taken a very brief look at network management, but I do suggest that you stop the tape and look at section 3 in the supporting material. Currently, the majority of wideband services, such as Megastream, are transported from BT serving exchanges to customer sites using fibre and copper systems based on PDH technology. Over the years, several systems have been used, the most recent being known as DWSS, that's Digital Wideband Serving Section, and CWSS, Copper Wideband Serving Section. Where appropriate, DWSS and CWSS provision may continue for some time, but Access SDH systems will supersede all these systems for delivery of wideband services, that is, services at 2 megabits per second and above. But why is BT introducing Access SDH? Well, the principal business drivers are the continuing need to reduce costs and strong customer demand for SDH technology. Access SDH includes two key network elements: consolidation units or CUs and network terminating equipment or NTEs. Let's first consider the CUs. These will provide a new serving tier and are designed to be located at BT nodes. Initially, these locations will be existing core SDH sites. The CU will be connected to a tributary on a core add-drop mux so that circuits may be routed over the core SDH network. The CU will support connections with a number of customer-located NTEs. This connection is normally achieved using a single optical fibre, but can also be copper or, in the near future, radio. Copper delivery requires two pairs to provide a single 2 megabit circuit and utilises high-density subscriber loop technology, or HDSL for short. As you'll see shortly, there's a range of NTEs, and these provide the customer with the service interface such as G703 and X21. The CU also has 2 megabits per second breakout. Services such as ISDN 30 and KiloStream N will make use of this facility, as it will allow circuits to be routed from a customer to other BT platforms at the CU node. At large sites, a hub mux may be utilised. This is basically a large CU and is capable of connecting a number of CUs to the core SDH network. It will also be capable of routing traffic from one CU to another, but will not be provided with a breakout facility, nor will it directly serve customers. Earlier in this video, we looked at circuit protection, so let's see how this can be achieved with Access SDH. In this first example, there's only one connection between the BT node and customer premises, and therefore the link is unprotected. This is called single access and initially is likely to be the most common arrangement. A certain level of protection can be achieved by having two separate access links from the CU to the NTE, which could be diversely routed. This is known as dual access. Initially, most of the Access SDH equipment will not support dual parenting, and therefore full path protection won't be available until a later date. Now that you're familiar with some basic Access SDH principles, let's have a look at some real equipment. This is the Fujitsu CU and will be known in BT as the Shelf 7A. The shelf can be configured as a hub mux or a CU. If we look at the top of the sub-rack, you'll see the station interface area. This is modular in design and houses all the cables and electrical connections. The lower two shelves of the sub-rack contain the plug-in units. Here you'll find the common cards required to provide control and switching functions, and the line terminating equipment cards, which are provided reactively and selected depending on the type of access link to the customer. All these cards have a mechanical key to prevent cards being inserted into the wrong slot. Note that any optical connections are made on the plug-in units. On this CU, the 2 megabits per second breakout facility is provided by cards in the CU, and the breakout interfaces are cabled to the digital distribution frame. HDSL circuits may be served directly from the CU or from an HDSL shelf. Let's now look at the customer located equipment for use with the Shelf 7A. Well, there's a range of Fujitsu NTEs. Here's the front and rear of the 4x2 fibre NTE and the 16x2 fibre NTE. There will be a single 2 megabit HDSL NTE and a 34 megabit NTE in the future. Like the core SDH network, Access SDH is designed to be centrally managed. Over the coming months, these will be integrated with the existing SDH management systems. When this tape ends, you may find it useful to have a look at section 4 in the supporting notes. There you'll find information on Access SDH and information regarding further training. I hope you find this video and the supporting material a useful introduction to the world of SDH. It only remains for me to say thank you for watching.